In this video, I'm going to talk about basic properties of the graph of the sine function. Its domain, range, zeros, y-intercept, maximum, minimum, all those things. But first of all, what does the graph of the sine function even look like? Well, let's find out. Here we've got a unit circle, and we're going to use this unit circle to draw the graph of the sine function on these axes. So the unit circle gives us a bunch of angles and a bunch of points on the unit circle. And remember, we've learned previously that the y-coordinate of those points corresponds to the sine of the angle. So we can use this unit circle to construct a table with theta, our angle, and sine theta as a function of theta, and that's just the y values. Theta we get from the blue angles, sine theta we get from the red y values, all throughout the unit circle. And we can use this information, just put it right on this graph to see what the graph looks like. So starting out, when theta is 0, sine theta is 0. So that corresponds to a point right at the origin. Okay, so now when theta is pi over 6, sine theta is a half. So we move a little bit to the right. Let's make a mark for pi over 6. Put that really tiny. Pi over 6. When theta is pi over 6, sine is a half. So we're up to our halfway point right here. And then when theta is pi over 4, so let's make another mark right there, pi over 4, we are up to root 2 over 2, which is a little bit above the halfway point. So right about over here. Then when theta is pi over 3, don't have room to write it, but let's make a small mark for pi over 3. We're at root 3 over 2, which is getting pretty close to the value of 1. And then at theta is pi over 2, that's this right here, we actually reach the value of 1. So we've got kind of an upward slope up here that starts off our graph of sine. So let's connect the dots here. Okay, so there's our upward slope. And what happens next? Well, from pi over 2 to pi, we're just going down in the same way that we came up. The y-coordinates are going to be the same, but now we're decreasing from 1 back down to 0. So this upward slope is going to be followed by a downward slope back down to 0. And then what do we do next? Well, now we go from pi to 3 pi over 2, and we start at 0, and then we're going down to -1. And again, it's the same y values, but now they're negative. So this curve is going to be symmetric like the one before, but going in the negative direction. So it'll look like this. And then we're going back up. So go back up here. And then there we are. We're back where we started. Now, since we're back where we started, we just repeat the process again, going from 2 pi to 4 pi. And then again, going from 4 pi to 6 pi, and so on and so on. So this function is just going to repeat itself. It's going up like before, and then down like before, then down some more like before, then up like before, and it just goes like that forever. Alright, so likewise, it's also repeating itself on the negative side. 0 is the same as -2 pi. So at -2 pi, we're starting out at 0, and we're repeating, doing the same kind of thing, going around to -pi, and then around to 0. So let's go up, down, down, up. So that's repeating itself. And then another angle that's equivalent to 0, not only -2 pi, but also -4 pi. If we keep going backwards 2 pi from 0 each time, we'll be in the same place that we started. So if we start at -4 pi, then we also have the same kind of curve going on. Up, down, down, up. So the graph of sine just keeps doing this up, down, all the way to positive infinity and all the way to negative infinity. Alright, so now that we know what the sine function looks like on a graph, let's start talking about its basic properties. We'll start off with domain and range. So what is the domain of the sine function? Remember, domain is just all the valid inputs to the sine function, or you can think of it also as all the places on the x-axis where the function is defined. So where does it cover on the x-axis? Well, it covers the full x-axis. It goes on for infinitely long in the positive direction, and it goes on for infinitely long in the negative direction. So it really just covers all the x. So it covers all real numbers, and we can write that by writing that domain is x is in the real numbers. X is in the set of real numbers. All right, so how about the range? Where did the outputs cover? The range is all the possible outputs of the sine function. And if you look, it's oscillating between -1 and 1. -1 is where the valleys are, and 1 is where the peaks are. And it just covers all the numbers in between. So the range then is just the interval from -1 to 1. So we can write that as y is in the interval -1 to 1 using brackets, because it can attain the value of -1 and it can attain the value of 1. So there's our range. Now let's talk about the zeros and y-intercept of the function y equals sine x. So looking at the zeros, we've got a 0 here, a 0 here, a 0 here, a 0 here, here, every time it crosses the x-axis. And do you notice a pattern in all of these zeros? Well, they occur at all the multiples of pi. Look, there's pi, there's 2 pi, there's 3 pi, there's also, we can write 0 pi for 0, we've got 0 pi, there's negative pi, which is like -1 pi, -2 pi, -3 pi, so it's just any integer times pi is a 0 of this function. So how we write that is write that the zeros are x equals n pi, where n is an integer. So n is in the set of integers. All right, and then the y-intercept, that's a little bit easier. That's just asking what do we get out from the function when we plug in 0 for the function. So when we plug in 0, we get out 0 because it just passes through the origin right here. So the y-intercept is just 0. Now let's talk about the maximum and minimum of the sine function. So the maximum occurs at the peaks here, at the very tops of the peaks. So that's these points here. And we see that those points occur at a y value of 1. So our maximum is 1. But where are the x values at which those maxima occur? That's a little bit trickier to write down. So first of all, there's the simplest x value is probably this one here. We can see that's halfway between 0 and pi. So that's just at pi over 2. So we've got pi over 2. And now how about where does the next one occur? Well, that one is at the next one. So add 2 pi. You can also think that the maximum is right in between 2 pi and 3 pi here. So it's like the average of them. So you can add them together and then divide by 2. So 2 pi plus 3 pi divided by 2 is just 5 pi over 2. And then there's also a maximum over here. So we can do -2 plus negative pi is -3 pi, then divide by 2. And that is -3 pi over 2. So here are our maxima, here, here, and here. And what we're really doing is we're just starting at pi over 2, and then we're stepping 2 pi in both directions. So adding multiples of 2 pi and subtracting multiples of 2 pi. So we can say that the maximum occurs at x equals pi over 2 plus 2 pi n, where n is an integer. So where n is in the set of integers. So that takes care of pi over 2 because 0 is in the set of integers. So you plug in 0 here, you just get pi over 2. And then if you plug in the positive integers, like 1, 2, 3, and so on, you get the maximums on this side, on the positive side. If you plug in the negative integers here, you get the maximums on the negative side. Like if you plug in -1, then you get pi over 2 minus 2 pi, which is just that coordinate right there, -3 pi over 2. So now that we've done the maximum, the minimum part is going to be a little bit easier. Let's identify the minimums first. That's just at the very bottoms of the valleys here. So there, there, and there. And we can see that they all have a y-coordinate of -1. So that's our minimum. Our minimum is -1. And now where do these minimums occur? So let's write occurs at x equals what? So let's see. So the easiest one to think about is this one right here. That's just halfway between the origin and -pi. So that's just -pi/2. And you could also see that by just taking the average of 0 and -pi. 0 plus -pi is -pi divided by 2. And we'll do that same idea to find the rest of the minimums. So going to this one over here, you can just add them and divide by 2. Pi plus 2 pi is 3 pi, then divide by 2, you get 3 pi over 2. And then there's also one here, so -3 pi plus 2 pi, plus -2 pi is -5 pi, then divide by 2. So -5 pi over 2. But essentially what we're doing is we're just starting at this -pi/2 and then stepping 2 pi in either direction. Step +2 pi, the next one would be at another add +2 pi, and then you could also go backwards 2 pi, subtract 2 pi. And so the way we're going to write that is we're starting at -pi/2, and then again we're just adding multiples of 2 pi, so plus 2 pi n, where n is an integer, so n is in the set of integers. 0 is in the set of integers, so we get our -pi/2, and 1, 2, 3, 4, so on are in the set of integers, so we get the ones that go -pi/2 plus 2 pi, then we also get the one that goes plus another 2 pi, because that's n equals 2, plus another 2 pi, n equals 3. And then for the negative integers, we've got our minimum points that are going backwards, -2 pi, minus another 2 pi, minus another 2 pi after that, and so on. So now that we've talked about some properties of the sine function, it's quiz time! Which of the following plots is the graph of y equals sine x? Can we identify the graph that is actually the plot of y equals sine x? There are 3 plots here that are not right, and only one of them is right. So which one? Why don't we start by eliminating some plots? Let's look at this one here. So this plot, do you notice anything peculiar about it? Well, one thing, the first thing we talked about was the domain of the sine function, and we established that the domain was all real numbers. So that means that the sine should cross, it should cover all the x values here. But in this graph here, we're only covering the positive x values. We should also have the graph go to the negative x values as well. So yeah, this definitely isn't the graph of sine. Okay. Now, all the other graphs cover all the x values. Why don't we take a look at this one? So remember we talked about the zeros of the sine function, and we said that the sine function should have zeros at multiples of pi. But hold on, what about the 0 here? Shouldn't it have a 0 there? Pi and 3 pi and -pi and -3 pi? It has zeros at 2 pi and -2 pi, but it looks like it's missing some of the zeros. So yeah, this isn't the graph of y equals sine x either. Okay, how about these two? Now these look pretty similar. Looks like pretty much the same graph. What's the difference here? Well, the difference here is just the ranges here. Here we've got pi and -pi. Here we've got 1 and 1. And which one of these is the correct range for sine? Well, think about the unit circle. The y values only range between -1 and 1. It's not -pi and pi. Pi is for the angle, not for the output. So nope, not this graph either. And that leaves us with this one. So let's just take a look at this one and make sure that it's not a trick question and that this one is actually the one. So we checked that it has the right zeros, it has the right range, it has the right domain. How about the right y-intercept? Yeah, that's at the origin, 0. Good. And how about the right maximums? Maximums are the peaks here, and we've got one at pi/2. Great. And then plus 2 pi this way. Yeah, that looks good. This way also, this way. That looks good. And then how about the minimums? So minimum at negative pi over 2 over here, and plus 2 pi this way, plus 2 pi this way, minus 2 pi going this way. Yeah, it all looks good. So this one right here is the graph of y equals sine x. In the future, we'll also learn about other properties of the sine graph, such as its period, and we'll also learn how to graph sine functions which are shifted horizontally by some amount.